Welcome to the third video for part one of our lecture video series for Friday, May 5th, where we are practicing again with our warm-up, another example of how to use and apply the ideal gas law. So we were told in this example that we have a sample of gas at standard temperature and pressure in a piston. So remember, a piston is like what you would see with a syringe. This is just a container that is sealed but yet movable. So let me draw this a little bit lower down. All right, so we've got our gas inside this piston, and we are at standard temperature and pressure. Okay, so there's a couple of things to know about standard temperature and pressure. So remember, standard temperature is 0 degrees C, which is 273.15 Kelvin. Standard temperature, and at standard pressure, this is 1.00 atmosphere, and I forgot to include some information here, so let's do 1 mole, 1.00 moles of a gas. At STP is in a piston, and then we are going to heat the gas in the sample, which is going to allow the piston to adjust as our gas expands. And let's think about how that piston would adjust. So we know that as we increase the temperature, we are adding more thermal energy and thus kinetic energy into our system. That is going to allow for a higher frequency of collisions. It's going to be pushing up against this piston, causing the piston to move upward, and our volume will expand. All right. So we've got 1 mole of our gas at standard pressure and temperature. And then we are told that our new conditions is that our temperature is 25 degrees Celsius. And we need to think about what's going on with pressure. So because this piston system is able to move, right? It's not a rigid container. We are going to find that the moles of gas at this new temperature have expanded the volume such that the pressure remained constant from start to finish. If we were able to keep the volume capped, right, if we had this in a rigid container where the container could not compress or expand with our gas, then the pressure would certainly go up. But here, because the volume is adjusting to the increase in temperature, the pressure is going to remain the same. Okay, got 1 mole of gas, right? That is not something that is changing. This is a closed system. And what we want to figure out is the new volume. So this requires us to remember something special about what happens at standard conditions. So 1 mole of gas at standard temperature and pressure, if you recall from our practice problem at the end of Wednesday's lecture, occupies a volume that is 22.4 liters. So this new volume that we do not know, because we are now no longer at standard temperature is what we're trying to find. So let's set up our ideal gas equations. So we've got general PV over NT is equal to R, and since R is a constant, I can say that the pressure and volume and moles and temperature at some initial condition is equal to some pressure and volume and moles and temperature at some new condition. And I can set these equivalent because these are both equal to R. Now let's ask ourselves what is changing. So what is changing? So we see that temperature is changing, and as a result, volume is changing. Which means that what is constant is going to be our pressure and our moles. Why is this something that's worthwhile to do? Well, if pressure is constant, then the pressure initially is equal to the pressure finally. And if the moles are constant, then the moles initially are equal to the moles finally. Meaning that if I were to go back to this expression here, I would cancel out P1 and P2 because they're the same number. And I would also cancel out N1 and N2. This leaves us with V1 over T1 is equal to V2 over T2. Hey, this is one of those non-pressure gas relationships that we derived using common sense on Wednesday. So this is why I like to use the ideal gas law for kind of every gas problem where it's relevant, because I can always get the more simple gas relationships from the one that includes everything, the ideal gas law. So let's apply this down here. So V1, this is our 22.4 liters. At T1, that was our standard temperature, 273.15 Kelvin. This is equal to V2, which we do not know, over T2, so that was our 25 degrees Celsius, so that's 298.15 Kelvin. So if I want to solve for just V2, that's going to be 298.15 Kelvin times 22.4 liters over 273.15 Kelvin. This will leave us with Kelvin canceling, thus giving us our unit of liters, which we want. And because we had our temperature go up, we would expect for the gas volume to be larger. So let's see if we get that. So 298.15 times 22.4, excuse me, over 273.15. Okay, this gives me a new volume of 24.5 liters. And is this larger than it originally was? Yes, it is. So V2 is 24.5 liters. Okay. So now that we are well acquainted with the ideal gas law, the idea of partial pressure, and how we can use the ideal gas law to get kind of more simple relationships between gas properties like volume, temperature, moles, etc., let's now get into gas stoichiometry. So we're going to be doing some more practice problems where we look at using the ideal gas law, but instead we're now going to be looking at using the ideal gas law as a means to get moles so that we could do some kind of stoichiometry for a chemical reaction that involves a gas. So that's coming up in part 2.